Okay, lesson 1.5, solving absolute value inequalities. And the lesson is no different than the others. We still have the same mnemonic. Don't forget ISS, isolate, separate, and solve. So we'll start with the basic one we've already covered. Absolute value of x equals 2. So we know that our first step is always to isolate the absolute value bars, meaning to get them by themselves on the left side of the equation. Absolute value bars are already alone. Our next step would be to separate. So we would know that our answers would be x equals 2 or x equals negative 2. Last step would be to solve. In this case, we don't really need to solve, seeing as x is already by itself. So here are our two answers, x equals 2 and x equals negative 2. However, this lesson is talking about inequalities. Remember, inequalities, those are your greater than, less than, greater than or equal to, less than or equal to signs. Don't forget, we're going to need this, the smiley faces that I gave you in a few of the last lessons. Open dots for greater than or less than signs, parentheses. Closed dots when they have equal to, and we use brackets. Okay, so if we're using our greater than, less than signs, here is another small example. Absolute value of x is greater than 2. Now the steps are basically the same. Isolate, separate, solve. One change. When we separate, we're going to have x is greater than 2, or, remember, we always flip the negative, so if it's positive, we would make it negative. The other thing that has to change with inequalities is you flip the sign. So when you do your separate stage, yes, one becomes positive and one becomes negative, but on your second equation, you flip the sign. Here are your two answers. Lastly, if we have absolute value of x is less than 2, it works the same. So our absolute value bars are already isolated. To separate, we would have x is less than 2, or x is, flip the sign, greater than, negative 2. So again, no matter what the sign is, on your separate stage, you have to flip the sign and change it to a negative. We've already done the negative before, but just to reinforce that. Now with this lesson, we're also going to have to graph these. So here, let me go ahead and, now you guys know I'm not really picky about your graphs. Just make sure that you have pretty much all the numbers on there in 0. So my lowest number I have here is negative 2, so I'm going to put that on there, 0, and the other number is positive 2. Now for graphing. I have a mnemonic that's called less than or greater. So in order to graph these, we're going to look at the original sign. So in this case, this was a greater than sign. So my mnemonic says greater because it's greater than. Greater than is greater. And what this means is we're going to encompass a couple of few different things here. So we've got our greater than sign, which tells us automatically that we'll need open dots. So above my negative 2 and my positive 2, I'll need an open circle. Or means opposite. So anytime you land at greater, that means your arrows are going to be going in opposite directions. Now, the last one. Again, we have negative 2 and positive 2, so I'll put those on the graph. I have a less than sign. Less than sign, it does not have an equal to, so that tells me automatically I'll also have open dots. Oh, I should have done that in green. Aw, I don't like it when it's not looking the same. Now, less than, that's my less than sign. It is less than. less than. And means between. So or means opposite. Your arrows are going in opposite direction. And means in between. So your graph is always going to be determined by your original inequality sign. Okay, if you have this little sheet of paper, I want you to glue it in right below here, and we'll talk about that. All right, basically this little sheet of paper has the exact same information on it as what I just told you. But let's take a look at it anyways. Okay, here is, these two are both greater than signs, and we talked about greater, and so you'll notice that here it is or. The next thing I just want you to notice is what the graphs look like whenever it's or. Or means your graphs are going in opposite directions. Your arrows are pointing in opposite directions. The only difference between these two graphs is the open and closed circles. Again, you'll notice that that comes from the original greater than sign. One has a bar underneath it. That means we have closed circles. Again, we know this stuff. Less than sign. Notice that it says and, less than. I also want to point out that the graphs are in between. So whenever you see the word and, you know that it's and, your graph is connected on the inside. On the greater, I want you to also make yourself a note that says or means opposite. Or means opposite. All right, practice problems. Let's solve some. Example 1. Absolute value of x plus 7 is less than or equal to 2. So steps don't change. First step, isolate. Absolute value bars are already isolated on the left side. So we're pretty much good there. I'm going to skip down to the second step, which is separate. Separate is x plus 7. Again, we're going to leave the sign for the first one. It's less than or equal to 2. Or x plus 7, flip the sign, greater than or equal to negative 2. One more time, whenever we separate, one's going to be positive, one's going to be negative. Really, the only thing new I'm teaching you here is to make sure that you change the sign on the second one. Lastly, we're going to solve. Whenever you go to solve these, solve them just like you would anything else. Just pretend like this is an equal sign while you're solving. We want to get x by itself, so we'll subtract 7 from both sides. 7's cancel, and I get x is less than or equal to 2 minus 7 is negative 5. Got to do the same thing with our second problem. We'll subtract the 7 from both sides. 7's cancel. X is greater than or equal to negative 2 minus 7 is negative 9. Now graphing this, set up your number line. The smallest number, remember, is always the one to the left. Don't forget, negative 9 is smaller than negative 5. Negative 9, and then negative 5. 0 is up here. Okay, looking back at our original sign, we have a less than or equal to. That tells me that whenever I go to graph, I need closed dots. Again, looking at the original sign, this is a less than. Less than. Less than tells me that my graph needs to be connected. The last thing we need to do is write write an inequality statement for this, and we've done this before. Remember how I taught you that your line is also known as x? And in order to write your graph in inequality form, we'll write the smallest number first, which is -9. X is literally in the middle, and the biggest number, which is -5. And then we just need our inequality. Less than or equal to, less than or equal to. Okay, example 2. Absolute value of 2w minus 1 is less than 11. I want you to pause this video and complete this problem on your own. If you have any questions, I want you to refer back to example 1. It's going to work the exact same way. Don't forget to graph it and give your inequality. Okay, first step, isolate. Absolute value bars are already by themselves on the left side of the equation. We can move on to our separate stage, which would be 2w minus 1 is less than 11, or 2w minus 1, flip the sign and make it negative. Last step is to solve, in other words, getting w by itself. I'll add 1 to both sides. My 1's cancel. 2w equals, less than. 11 plus 1 gives me 12. Divide both sides by 2. This makes my 2's cancel. W is less than 12 divided by 2 gives me 6. Solving the second equation, we'll add the 1 to both sides. I get 2w is greater than -11 plus 1 gives me -10. Dividing both sides by 2. W is greater than -10 divided by 2 is -5. Here are your two numbers. We need to graph those on our number line. Remember, the smallest number goes first. You guys, negative numbers are always smaller than positive ones. According to our signs, we have, they're not included, so we're going to need open dots above our numbers. We're going to have to refer back to our original equation to determine if we have less than or greater. This is a less than sign, which is less than, again, which means our graph connects. Lastly, we need to write our inequality. It is literally written as it appears on the graph. Remember that x is your line. So we have -5, x is in between, and then your biggest number is 6. Your original inequality is your less than. Okay. Example 3. Again, I want you to try this one on your own. The problem is absolute value of q over 3 is greater than 2. So pause this video and try this one by yourself. Isolate, separate, solve. Give me a graph and a final inequality. And come back and see if you got the correct answer. Isolate, absolute value bars are already by themselves. I'm good. I can move on to the separate stage. Separate, I've got q over 3 is greater than 2, or q over 3 is, flip the sign, less than -2. All right, getting q by itself. I have to get rid of this 3. In order to do that, I can multiply the whole equation by 3. Whatever I do to one side, I have to do to the other. When I do that, these 3's cancel, and I have q is greater than 2 times 3, which is 6. Or, working the second problem, same thing, to get rid of the 3, I can multiply the left side by 3. Whatever I do to one side, I have to do to the other. My 3's on the left cancel. Q is less than -2 times 3 is -6. Graphing this guy. Smallest number, -6, then 0, then +6. I have just regular signs without bars underneath. That means I will need open dots. Going back to my original inequality to figure out if I have less than or greater. This is a greater sign. This tells me or. Or means opposite. My arrows should be going in opposite directions. Now, writing your inequality. This goes back to lesson 1.1, I think. You have two x's because you have two lines. Anytime you have two x's, you're going to have an or statement, meaning you have two x's in your inequalities as well. So we're going to have x in our -6. This line is pointing to the numbers that are less than. They are smaller than -6. So I have less than. Or, I got my x in my +6. This line is pointing to numbers that are greater than 6. So I'll need a greater than sign over here. Anytime you have two x's, your final inequality will have an or statement. Keep that in mind. This is your inequality statement. Okay, example 4, I'm going to work this one with you. We have 4 times the absolute value of 2x minus 5 plus 1 is greater than 21. Okay, first step is to isolate. If you'll notice on the left side of the equation, the absolute value bars are not by themselves. There's a 4 that's keeping it from being by itself, and there's a 1 that's keeping it from being by itself. We're going to have to get rid of both of those things before we are isolated. First thing we'll get rid of is this 1. To move it to the other side, we'll just subtract 1 from both sides. And I'll make this cancel, and I've got 4 times the absolute value of 2x minus 5 is greater than 21 minus 1 is 20. Now keep in mind this 4 is being multiplied, so to get rid of the 4, I'll have to divide both sides by 4. Now my 4's cancel, and I get absolute value of 2x minus 5 is greater than 20 divided by 4, 5. Now the absolute value bars are by themselves. Notice the difference. They were not alone at the beginning of the problem. Now they are. Once they are isolated, we can move on to our separate stage. So we have 2x minus 5 is greater than 5, or 2x minus 5, flip the sign, -5. Lastly, solve. We'll add 5 to both sides. I get 2x is greater than 5 and 5 is 10. Divide both sides by 2. X is greater than 5. I'm going to do the same thing with the second equation. We'll add 5 to both sides. The 5's cancel, and I have 2x is less than -5 plus 5 is 0. This is fine, just keep going. We've got to divide both sides by 2. X is less than 0 divided by 2 is 0. Let's graph this. We've got our two answers. So I've got 0 and 5. Okay, looking at our inequalities, we're going to need open circles. This is just greater than, that means open circles. Original inequality, back at the top. This is a greater sign, greater. That tells me that my arrows need to go in opposite directions, or means opposite. Now in writing your final inequality, notice that you have two x's. That means you're going to have two x's in your inequality statement. Why don't you pause the video and come up with an answer and come back and see if you get it correct. Okay, so the first one, we've got x and 0. This is pointing to the numbers that are less than 0, which is a less than sign. Or we've got x and 5. And our inequality here is pointing to the numbers that are greater than 5. You guys keep in mind this is a number line. Numbers to the right are always bigger. This is going to be 5, 6, 7, 8. I just do my number lines like this because it takes me less time, I guess. Greater than 5, so we just need a greater than sign. This is your final answer. Okay, let's take a look at example 5. We've got absolute value of 8x minus 1 is less than -2. Now I want you to think about this for a second. Absolute value less than a negative number. What numbers are less than negative ones? Negative numbers are less. So is absolute value ever going to be negative? No. Absolute value is always going to be a positive value. Positive numbers will never ever be less than negative ones. The answer to this is no solution. No solution. Make yourself a note of why this is. This absolute value will never be negative. And negative numbers, not negative. This will never be negative. And positive numbers are never less than negative ones. Absolute value will never be negative. That means this is going to be a positive number. Positive numbers are never ever less than negative ones. There's no possible answer here. What about this one? Example 6, absolute value of 10 minus m is greater than -2. Absolute value, we just said, is always going to be positive. When are positive numbers greater than negative ones? I hope you said always. Positive numbers are always greater than negative. That means no matter what this number is, this statement will always be true. Your answer here is all real numbers. Any number you put in there is going to work. All real numbers. Because absolute value is always positive, and positive numbers are always greater than negative ones. So, write yourself another note. Absolute value will always be greater than a negative number. So question, how do you know when to watch out for these things? Because we can have no solution or we can have all real numbers. A dead giveaway is as to when you should be concerned is if you have absolute value bars and negative numbers. Absolute value bars and negative numbers. So keep that in mind. Anytime your absolute value bars are isolated and there's a negative number on the other side, you need to be careful. Okay, last one. You should have another glue in. I'm talking about a computer. So have this guy and go ahead and get that glued in for me. All right, it says you are buying a new computer. The table shows the prices of computers in a store advertisement. You are willing to pay the mean price with an absolute deviation of at least $100. How many of the computer prices meet your condition? Absolute deviation of at least. That is going to come in handy. Now, we are going to need an absolute value equation. So I've given you this before. Remember, we have absolute value of x minus the halfway point equals the distance. Now you may also recall that I said, hey, you need to write this down because it will change. Sometimes they refer to the halfway distance as the mean, and sometimes they refer to the distance as deviation. And in this case, that is true. So we need to write an equation that goes with this. We got to have your mean price or your halfway point. Remember, that's going to be your A plus B divided by 2. So we've got 16. We got to find your lowest price on here. So my lowest price is going to be, can't find it. I'm sorry, I'm thinking of something different. Mean price, that's just adding up all that's your mean, your average. So you can add all of these numbers up and divide it by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Add them up, divided by 10, so we'll get 6,640 divided by 10. That gives you a mean price of $664. Sorry about that. So I have my mean price, and then it already says my absolute deviation of at least $100. So it tells me what my deviation is. So I've got my mean. I'm going to go ahead and plug that in. X minus $664, and then my deviation of 100. Now, this is an inequality, so I need to know which inequality sign to put here. This says at least. That means I'm not willing to pay more than $100 in deviation. So that means all of this has got to be less than or equal to 100 because I don't want to pay it if it's more. And from this point, you can separate and solve. So we'll separate it. We've got x minus 664 is less than or equal to 100. Or x minus 664 is greater than or equal to negative 100. Solving for x, we'll add the 664 to both sides. So I get x is less than or equal to 764. And same thing here, add my 664. and I get x is greater than or equal to 564. So looking back at my original inequality here, I've got less than. That means and. So that means my x is literally in the middle. So I write my smallest number first, with x in between, and then my largest number. And then we know it's got to be less than or equal to for each of these. So this is the amount of money, this is what I am willing to pay. It's going to have to be, I'll pay a minimum of $564 and a maximum of $764. The original question is how many of the computer prices meet your condition? So how many of these prices are between $564 and $764? Well, I've got one here, one here, one here. One at $750, $670, and $650. 6 different computers meet the condition. All right, just a recap of what we did here. Table shows the prices, and we are willing to pay a mean price with an absolute deviation. Again, when it comes to absolute value equations, we know that the halfway point is also known as the mean. The distance can also be known as the deviation. So all I needed to do was figure out what the mean was, since they already told me the deviation was 100. So in order to find the mean, literally just find the average, add up all of the possible computer prices, which was 6,640, divided by 10, because there's 10 prices here. That gives me a mean of 664. So now I have the mean, which I plugged into my equation, and the deviation, which was 100. It said at least. That means all of this has to be less than or equal to 100. It can't be more than 100. I don't want to pay that. That's how I got my less than sign. Once I have an equation, I can solve. We did our, we were already isolated, so we did our separate stage, remembering to flip the sign, and then we solved, getting our two numbers, 764 and 564. The original inequality was less than. So when I went to write my inequality, I knew that there was going to be an x in between the 564 and the 674. This tells me what I am willing to pay. This is your price range. Lastly, all I did was I went to see how many of those computers fell between this price range. If you have any questions, please go back and review the video again. Stop me, make me go forward, whatever. Ask somebody around you.